Well, thank you for that introduction. Sorry about the confusion. I'm Rob. I'm the CTO and one of the co-founders of QphoX. We're a startup based out of Delft in the Netherlands, trying to build the tools that will hopefully enable modular networks of the most powerful quantum computers. So it's really great to be here. So I feel like I'm preaching to the choir a little bit, but I wanted to give a bit of a vision into, say, what QphoX's mission is. So, there's been incredible developments and great strides made in quantum computing, kind of powered by the impact of this really disruptive technology. But it's the field still faces challenges to really kind of climb the hill of commercial applicability. And one of those challenges really is down to isolation, isolation between systems, which results in roadblocks in the development. Naturally, one of the biggest isolations is between different qubit modalities, but also for certain qubit modalities, especially ones based on microwave frequencies like superconducting qubits and quantum dots, there's isolation between modules, so they're kind of confined to these monolithic cryogenic environments. These are the isolations we're trying to remove and the roadblocks we're trying to overcome at QphoX. So that's why it's so excited to join you guys there at this event and hear about strategies towards modular and network computation. So a little bit more about QphoX. So we're a hardware company, basically trying to develop the tools that allow you to grow the size of quantum computers and network them together. At its heart, we're trying to build scalable interfaces between telecom, wavelength light, and quantum systems, really by taking all the decades of progress we have in superconducting MEMS and photonics nanofabrication. The devices we're trying to create, they have to be bidirectional and coherent in order to transfer quantum information. And really, we're focusing on three main frequency bands: the microwave frequency band around 5 gigahertz, the optical telecom band at 200 terahertz, and then the visible optical band at higher frequencies. So if we can transfer information between the 5 gigahertz band and the 200 terahertz band, this is really what will allow us to network together quantum systems that were previously isolated. And if we can transfer information between the 200 terahertz telecom band and the visible band, we could now bring optical quantum memories onto telecom networks, but also we could start to actually realize that longer-term goal of bringing these different hardware modalities together in a single system. So with that in mind, I wanted to focus a little bit more tightly on our link between microwave and telecom bands. So this is a zoom in on one of our devices. And this transfer from microwave to telecom is obviously so important because it's what allows us to bring the quantum information outside of the cryostat and start networking it together through fibers. But if we want to do that, we need to interconvert a single microwave and an optical photon. This means we need to co-locate the two fields together and enable really strong interactions between them. And this is really the technical challenge that we've been tackling really at QphoX. And our approach here to convert these frequencies is actually to use a gigahertz frequency mechanical mode as an intermediary. This allows us to separate the microwave and the optical fields from one another. And then, crucially, it enables much stronger interactions. So from the microwave to the mechanics, we have piezoelectricity, and from the mechanics to the optics, we have photoelasticity. And these interactions are much stronger than the direct electro-optic effect you could get. As a result, this means that we can get efficient conversion between microwave and optical photons with much smaller optical power than you would otherwise need. It also means that actually we can operate with a relatively high bandwidth, which for these systems means into the tens of megahertz at microwave frequencies. Collectively, this low power and this high bandwidth means we can have as many of these devices as possible running as fast as possible in a single dilution fridge, where heat load really comes as a premium. So we've been working hard at these devices. They've made huge amounts of progress over the last 10 years, and they're now at the point where they can start to transfer single photons from microwave to optics. So then we have to turn to the key application of this technology, which is to enable entanglement between distant qubits. To do that, we need to take our transducer and connect it at the mixing chamber of a dilution fridge to a qubit. And then we can upconvert a single photon from the qubit, or maybe we could create an entangled microwave optics photon pair in the transducer. Either way, we can end up with an optical photon, which is entangled with an excitation in the qubit. If we do this on another system and we take the photons, mix them on a beam splitter, and detect 1 or 2 photons after the beam splitter, we can then project the photons into a highly entangled state. This process is due to optical losses. It's probabilistic, but fundamentally, thanks to the heralds, the losses don't negatively affect the fidelity of the entanglement that you can create. There's a few references here, a paper we published basically covering kind of the core platform we work on, another paper that was published earlier this year where we looked at an application of this technology to read out qubits from Rigetti computing. And then finally, a white paper we recently published where we kind of map out what you could do with this technology. But in many ways, this is just the first step. We have this probabilistic single channel entanglement, but we need to convert to a point where we're actually generating lots of entangled pairs between multi-qubit computers. And the way in which we need to do this, as Claire said, we need to build entanglement factories that are constantly churning away, producing as many Bell pairs as possible between these systems. If we want to do that, we have to optimize 3 figures of merit. The fidelity of the entangled state we can create, the rate at which we can create it, but also the number of channels we could simultaneously realize between the computers. To date, most work has really just been on single device performance, pushing the efficiency and the noise of these microwave to optics transducers. And this is how we could improve the fidelity and the rate of these links together. But even with a certain device, we still have a lot of freedom to do different things by choosing a different entanglement protocol or pumping the system harder. We can actually start to trade off between the fidelity of entanglement we produce and the rate at which we produce it. But this still keeps us in this single channel picture. If we want to move to multiple channels, we don't want to focus so much on, say, the core device, but really how well we can integrate these devices inside the dilution fridge. There we need to focus on basically the heat load of the device and our ability to parallelize it, say through multiplexing, so we can have many of these devices operating in parallel. But now, once we can do that, we can open up new avenues for optimization, where we can have multiple physical channels effectively producing one link, trading off the number of links and the rate of entanglement. So to take kind of more of a concrete example, if you were to try to entangle superconducting qubits, you could reasonably attempt entanglement, say, at as fast as around once every microsecond. But these qubits, say, will store their information for really about 100 microseconds. So that's kind of the window of opportunity you have for generating entanglement in this system. And parallelization is a really important tool here to make the entanglement fast enough. Another tool we have in our belt is the use of optical memories. These could help buffer the link and maybe use some asynchronous measurement techniques to project the entanglement. But the conversion from the telecom band to the operating frequency of the optical memory does need to be good enough to get some gain in the performance. But put collectively, once we're generating entanglement fast enough, we can now basically start to deliver entanglement not probabilistically, not deterministically, but at predefined times where we know we can have a high fidelity entangled state. And this is where we can start really boosting the fidelity as well, basically through distilling multiple copies of the entangled state without losing rate in the link. And here we can really start to trade off the number of connections between the qubits and the fidelity. And this is going to be really important for crossing, say, the 99% fidelity threshold for superconducting qubits entangled over an optical link. So to kind of wrap up, where's the field now? We've got these quantum-enabled transducers, single photon links, which can create kind of single-channel probabilistic entanglement links. Next, we have to boost the rates, the fidelities, but almost just as importantly, the number of links we can realize, so we can move into this state of on-demand, predefined delivery time entanglement. And then we're really off to the races. We can distill to boost fidelity, and we can start teleporting first information, probably, and then gates across the network. So a brief insight into what we do. Thanks very much for listening, and look forward to answering your questions.